China to talk about his work mapping thermal habitat of ectotherms based on behavior thermoregulation in a controlled thermal environment.
Good morning, everyone. It's my honor to present this topic of mapping the microhabitat use of the lizard from a thermal landscape. And my name is Teng Fei. I'm from Wuhan University, and this study was financially supported by Wuhan University in China and also ITC faculty of Teng University in the Netherlands. And here is the organization of this short presentation. And after a short introduction, I will present you two approaches that we have used to model the spatial usage of lizards' microhabitat responding to a thermal landscape. And the first approach is a dynamic model, and the second is a static one. And in the second approach, we developed a thermal roughness index to predict the microhabitat use of the lizard. And these two models, they have their own pros and cons, and they can complement each other. And they are also both validated by animal experiments. The microhabitat usually describe the small-scale physical requirements of a particular organism. Which means you can see that as the home range of an individual animal. And the thermal environment in ecological studies are usually represented by air temperature alone, or surface temperature, or sometimes just elevation. But at the microhabitat scale, it is not so accurate enough. So in this study, we define the thermal landscape as the landscape pattern of the thermal environment, which combines the effect of all thermal sources, that's including the radiation, the convection, and the convection to the animal. And why we focus on the microhabitat of lizard is because on one hand, it can, the animal distribution and occurrence is the core question asked in ecology. Maybe this research can offer some clue to that question. And on the other hand, it can, in the context of global climate change, maybe knowing the response of animal to the thermal environment may provide us some scientific policy-making basis for reptile reservations. And here is our target species. It's called oscillating lizard, with the Latin name of Timon lepidus. And it's native to Spain, Portugal, southern France, and this is the largest lizard species in Europe. The adult body size ranges from 30 centimeters to 60, but 90 centimeters are also reported, but it's rare. Why we choose the lizard as our target species? Generally because it's very sensitive to environmental changes, so it can be a good environmental indicator. And it's widely distributed, so it's easier to catch. And according to literature, it's easy to handle, but according to my own experience, it bites. And it's simple structured, so it's easier to model. And most importantly, the ability of them to behavioral thermoregulation. The behavioral thermoregulation. By this, they can shuttle from different thermal environments, such as hot rocks, not so hot rocks, the cold shadows, shades, and to regulate its body temperature. Because people used to believe that the lizards are animals that they cannot actively control their body temperature, so they could attack a cold-blooded animal to them. But since 1960s, we know that's not true. A lizard can regulate its body temperature by repositioning itself. This is a figure that shows clearly the body temperature of a lizard in one day. You can see shortly after the bask under the sun in the morning, and it can maintain its body temperature it's maintained perfectly to a certain range, to a very narrow range. And this is the result of behavioral thermoregulation. And to model that, we wanted to model that. And more importantly, we want to model the spatial consequence of the thermoregulation. So we have a four-step methods. We plan to firstly monitor the thermal landscape. Then we model the body temperature of the lizard, responding to that landscape. Then we model the movement of the temperature. Movement of the animal. And by this movement, we map the microhabitat occupancy. So we start from the first one, we monitor the thermal landscape by an animal experiment, and we rented a terrarium in the reptile zoo in the Netherlands, and we configured the inside of the terrarium by positioning different light bulbs and heaters, radiators inside the terrarium. We created a diverse thermal environment inside the terrarium. And also a lot of different sensors are installed inside the glass box, including the air temperature sensors, the light intensity sensors, wind speed sensors, and there is one thermal imager, actually 3 in a row, thermal imagers to monitor the land surface temperature. In a word, we monitor the thermal landscape inside the terrarium. Also, there is optical sensors that recording the position of lizard from time to time. So we know exactly where the lizard had been to and the spatial usage of the lizard. This is the top view of the through the optical sensor. And this is the top view of through the thermal imager. This is the land surface temperature. The reddish color represents hotter surface temperature and blue is colder. Okay. So after monitoring the thermal landscape inside the terrarium, we try to model the body temperature of the lizard responding to the thermal environment. And we constructed a biophysical model to calculate the incremental change of body temperature of the lizard. By this model, the body temperature in real time can be predicted from 6 terms. That is from the solar radiation, inside the terrarium, so it's radiation, and convection, that is the air temperature, convection, that is the land surface temperature, and the convection, that is the air temperature. Long wave radiation, the energy lost by losing water, that is the respiration rate, and the metabolic rate of the animal. As this model has many input parameters, some of them can be directly measured, and others can only be estimated, such as the lizard heat capacity. So we measure, we estimate those parameters through the literatures. But by further improving the model accuracy, we calibrate the model by re-estimating those parameters and using a Monte Carlo simulation and compare the result with the animal experiment, and we adjust these parameters within a certain range. After the calibration, the model had done a good job on predicting the body temperature. This is the observed body temperature versus the predicted temperature. So you can see it predicted quite accurately. The accuracy in terms of root mean square error is less than 0.6 degrees Celsius. And here is simulating the temperature when the laser is heating up, and this is when the laser is cooling down. Okay. After modeling the body temperature, we can start to model the movement of the animal inside the terrarium. And a cellular automation-based model was applied here. And the assumption behind the model is quite simple. We assume a lizard will try to maintain its body temperature in daytime as long as possible. So the lizard will have a preferred body temperature, and it will maintain that temperature through movement as long as possible. So when the body temperature of the lizard fall below the preferred temperature, it will sense around within a certain distance and try to find the hottest spot to go at a chance of B. The probability P is assumed to be positively related to the difference between the body temperature and the preferred body temperature. That is, if the two values are apart greatly, that is, the lizard is too cold, and the motivation of the lizard to move to a hotter spot is strong. That is basically the concept of the model. That's when model is running, we simulate a small dot representing the lizard and move on the dynamic thermal environment. This is a snapshot. Okay. After we modeling the movement, we can map the microhabitat use. This step is quite simple, just by recording the places where lizard had been to, and we accumulated. So the habitat usage can be mapped. The first image shows the microhabitat use in 10 minutes. It's purely a simulation. And the second one is the microhabitat use in an hour. The third one is how a lizard used the microhabitat in 1 day. So you can see as the time goes by, the pattern emerges. But that's purely a simulation. From the experiment, the animal experiment, we have also recorded the locations of the lizard in reality. So we compare the two. So the upper one is the simulation, the lower one is the observation. So we can see a large portion of the microhabitat occupancy can be predicted using the dynamic model, but on some part it's not so accurate. Like in area C, we didn't predict any occupancy here, but the lizard did spend a lot of time in this position. Okay, then we can quantify that by classifying the occupancy to 3 levels: high, moderate, and low occupancy. And by this, the model can have the overall accuracy of more than 75%. So the result of the dynamic modeling, the approach 1, showed that simulating the behavioral thermoregulation of lizard by this approach may, to a large degree, predict the thermal habitat used by a lizard in a controlled environment. That's in a laboratory experiment, not. So we have to do another work on the natural habitat to test it. This approach has its drawbacks. The first one, this approach is a descriptive model, and it describes the mechanism on a lower level. In this case, the thermoregulation. It's a physiology level, and tries to explain the pattern emerges on a higher level. In this case, the spatial usage level. And this bottom-up approaches, they can never lead to any theory on the higher levels. And the other drawback is it is too slow, because it will iterate and simulate every second's body temperature change and movement. When we describe someone is really stupid or slow, we say it takes 2 hours for him to watch 1 hour. This is the case for this model. It takes 1 hour for the model to simulate 1 hour of lizard movement. So we need a faster way. That's why we consider later the second approach called we developed an index called the thermal roughness index by Laplacian of Gaussian filter. It was used to extract the thermal roughness from the image of thermal landscape. It is often used to find areas of rapid change in images, and usually be used to find the edges in the image. So in this case, by using this filter, we can select, we can find those places with great thermal diverse inside the thermal image. And the hypothesis of lizard will appear more at the thermally roughed area will be tested by an animal experiment in its natural habitat. And the field campaign was carried out at its natural habitat, not in a zoo or terrarium anymore. It was located in Andalusia province of Spain. And at the field area, the 2 sites were defined. Site one, we found a juvenile lizard, the same species there. And the snout vent length is about 37 millimeter. And an adult lizard was found at site 2 with a SVR of 270 millimeters. Also, the same species, Thymolepidus. And the same story, a lot of sensors were equipped to monitor, to observe the thermal landscape of the area. And one thing that was mentioned is a high resolution thermal imager was used to capture the land surface temperature, and we mount that on the top of a crane. It's about 10 meters high. And this is one image from that thermal image. And yeah, you can see there is a lizard here. And the thermal imager was set to take take a still picture for every 10 seconds because, to save the storage space. And those pictures will then identify, will then examined by human. Then we identify the location of the lizard when it appeared in the image. We mark it with a red cross, so we know where these locations the lizard had been to. Okay, then you see there's many red cross here, showing the spatial usage of the lizard in the natural environment. And it was compared with the thermal roughness index we proposed and extracted by the Laplacian of Gaussian filter. From this image, we can see compared it to at site 1 with the juvenile lizard. The thermal roughness calculated with window size of 7, this one, predicted the best the microhabitat usage of the lizard. These two are the most similar. And at site 2, the window size 11 is the most appropriate. So from the second approach, the results show the thermal roughness index offers a fast way to predict the lizard's microhabitat, its occupancy of that. If the moving window size to calculate the index is appropriate, and by the appropriate moving window size can be calculated, can be inferred from the reptile body size from further research. So now we have a dynamic way of modeling and a static way of modeling. They have their advantages. For the dynamic model, the advantage is it's accurate. It offers us a chance to understand the mechanism underlying, and it can simulate the dynamic process, and it's more transplantable because it's physically based. And for the static model, it's simple and fast, and it can function at large scale because it's fast. So, and it will lead some theory at a system level. And if we can combine the two models together and as their advantage, maybe we can simulate the maybe we can simulate the lizard distribution at larger scale, such as regional scale or the global scale. But that is our future work. Thank you.